Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, I am going to show you how to solve trigonometric equations. Now, this is the third lesson in our chapter for analytic trigonometry, and what we're going to work on is solving trigonometric equations on different intervals, as well as being able to solve trigonometric equations with multiple angles. So again, what I'm going to do is work through the notes that I've given to my class and provide them with some solutions and hopefully help explain for you how to solve different types of trigonometric equations. So what I did for kind of starting this lesson was I just wanted to remind students of some different ways that we can, solve equations. And so I kind of went back to like a little algebra 1, algebra 2 kind of type of problem and said, all right, how else can we solve this? And this was kind of a little bit of a brainstorming idea. And so what the students did, I just kind of like labeled some things. One thing you could do is just do a guess and check, right? So you could say, well, I know that the only numbers squared that are going to add squared to equal 1 are going to be plus or minus 1. The next one that students did was like the square root method. So they know that when we learned in Algebra 1, we talked about inverse operations, right? If I want to solve for x, I got to undo everything that's happening to the x. So one thing we talked about was undoing squaring by taking the square root. And this brought up again that fact of when you introduce the square root, you have to include the positive and the negative, because we already know there's positive in the 8, right? We know positive 1 squared is 1 and negative 1 squared is 1. So therefore, we had to remember that when we introduce that square root, not to make sure that we included the positive and the negative version. However, as we learned in Algebra 1 and Algebra 2, using inverse operations doesn't always work, especially when we have maybe more than one variable. So one thing that we kind of reviewed in this chapter, as well as in previous courses, was factoring. And we can solve by factoring by simply setting the equation equal to 0. So in this case, I only have one variable, so obviously the square root method would be a little bit more ideal. But again, my goal here is just to think of different ways that we could solve this. So if you subtract a 1 on both sides, you get an x squared minus 1 equals 0. So now we have an expression equal to 0. And the important thing that we teach about factoring is if we can, factoring is writing an equation as a product. So if I can write this expression as a product equal to 0, then I can apply the 0 product property. And I notice that this is a difference of two squares. So therefore, that's going to be x minus 1, x plus 1 equals 0. And now I can apply that 0 product property. So x minus 1 equals 0. X plus 1 equals 0. So x equals 1 and x equals negative 1. So that was something that, as a review, you can see it's a little bit more work, but not everything we can do with inverse operations. So that's why we practice a lot of the factoring technique. So that's where most students went ahead and were able to solve these algebraically. Now the next two techniques I'm going to use graphing. So one thing that we looked at is, if I had the equation x squared is equal to 1, if I wanted to graph this, or if I wanted to solve this by graphing, basically, if we remember, when we're trying to solve something by graphing, we're like, what do you mean solve it by graphing? So let's go back to this equation, like 0 equals, x squared minus 1. If I want to solve this by graphing, basically what I'm asking for is like, what values of x make this values or make this 0? And if you think about like when we graph on a, for instance, like an xy axis, right? So these represent the x values, so then this represents the y value. So when we're solving by graphing, basically what we're doing is we're trying to find the x values that when we plug them in for x, make y equal to 0. So we call those the zeros, the roots, the solutions, but mainly they're the x-intercepts, right? Because when y is equal to 0, that is going to be your x-intercepts. So what I could do is I could graph this equation and find where the graph crosses the x-axis. So I go down to 1, and hopefully you know the curve of a quadratic, over 1, over 2, up 2, at least the parent graph. And therefore we came up to those points. All right. So that was just, again, the reason why I'm doing this is because as we get into this next set, this is the technique that we're going to actually use to understand the solutions of the trigonometric equation. So that's why it's important. That's why I believed it is important to kind of go back through these and to remind the students of this. So on that next example is, again, rather than trying to think of setting this equal to y and finding the x-intercepts, another way we can think about this, again, the x-intercepts are x equals 1 and x equals negative 1, right? We already knew that. But the next way I wanted you to think about this is, well, if we know two things are true, right? If you remember systems of equations, the solutions are going to be where the two graphs intersect. So basically what we could do is we could say, well, what about if we set x squared equal to y and y equals 1. That means the solutions, the values that make that true, are going to be the points of intersection. So if I just go ahead and graph y equals x squared, which is rather easy, that's the parent graph, right? And then if I go and graph y equals 1, you can see that there's going to be 2 intersection points here, right? And of course, knowing what the shapes of those graphs, that's going to be x equals 1 and x equals -1. So obviously, guess and check is the best and easiest and quickest and fastest solution when you have something that's fairly basic. And we will use guess and check here for some of these problems. Then we get into using inverse operations. Like, that is very helpful when you just have a couple operations that you can undo. We will be doing that as well. Factoring is very important when you can't use inverse operations or guess and check, but however, you can set the equation equal to 0 and factor it. Therefore, factoring comes in handy. And then as far as the graphing technique, a lot of these equations, we don't want to set them equal to y. Like, this is important. This is helpful because, we talked about this in polynomials. But to understand these, we're going to use this graphing technique, and I'll be using this with graphing technology to understand our solutions. So let's go and get into the first example. So I kind of already did, I did 4 examples for my students, and I already kind of wrote them out. So I'm just going to kind of explain what I did, and then we'll look at the graph so you can understand what I did. And then I have multiple examples that I'll work myself through. So this one says, solve the following equations on the intervals. All right, so the intervals that we want to find our solutions is 0 to pi, 0 to 2 pi, and then all solutions. Now, the reason why we have an interval is important. I'll talk about that in a second. The main thing I want to kind of understand is let's just make a connection here with first solving as well as yeah, okay. So let's make a connection here with solving as well as make a connection here with solving and the unit circle. So in first points, if you remember, like we have an equation, right? So we're trying to find cosine of theta is equal to 1/2. Basically asking you the cosine of what angles is equal to 1/2. Now, one of the common misconceptions that students will make here is they'll say, well, why don't we use the inverse operations, right? Because if you take cosine of theta, and if you wanted to solve using inverse operations, you would use cosine inverse. Okay, and by using the restrictions of cosine inverse, that's only going to give us a solution of pi over 3. But the problem is that's not really what we're asking. We're asking for solutions that make this equation true. Now, on the unit circle, you can see that there's 2 angles that make this equation true. That's going to be pi over 3 and 5 pi over 3. But when we look at the graphical approach, if you remember, cosine actually goes on and on forever. So therefore, we have to figure out a way to be able to write all of the solutions. So that's how you can see in this case, I'll just go through from 0 to pi. That is actually the restriction of cosine. So you can see how that is limited, right? Or that's the restriction of that cosine inverse. So you can see how that's limited to just this angle, which is pi over 3. However, if I said find all the solutions on the interval 0 to 2 pi, which is basically the unit circle, you can see there's only 2 angles where the x-coordinate, right, cosine of angle gives the x-coordinate is equal to 1/2. And then for the last example is finding all the solutions. Now this one gets a little more difficult for students to understand. And the reason being is, remember the unit circle, like when we're graphing angles, like there's infinite many angles. Like we can continually go in around the unit circle. So if I have the angle pi over 3, if I want to get to another solution, I can just add 2 pi to it. By adding 2 pi, it takes me back to another angle that lies on a solution where the point on the unit circle, right, would be 1/2. Or the x-coordinate would be 1/2. So whatever angles you have on the unit circle, you can always add 2 pi to them to find all the solutions. And again, this will make a little bit more sense once we get into the graphical approach. But the main point I want to see is when you have a trigonometric equation, do not use the inverse operations because again, that is for evaluating an inverse function, right? There's only going to be one answer. Like an inverse function, you plug something in, you're going to get something out. But that's not always true for every, equation. Sometimes you're going to have multiple solutions to an equation. And that's exactly this case here for our trigonometric equations because there's infinite many angles that make this equation true. Pi over 3 plus 2 pi plus 2 pi. So the only reason why it's being restricted is because I'm restricting my solutions or I'm restricting the way I want my solutions to appear. So let's just kind of go through this next example and then we'll Actually, let's go and take a look at the graph, and then we'll come back to the next example. Okay, so here's the graph. And remember what we had is cosine of theta is equal to 1/2. So if I graph cosine, you can see here's the graph of cosine. And remember, it goes on and on and on for forever, right? So remember we talked about like the solutions to an equation is going to be the intersection points of cosine of theta and 1/2. So if you see here, like we just said pi over 3, 5 pi over 3. Right? And actually, if I just restrict this between 0 and 2 pi, which is basically the unit circle, you can see though, well, actually, before we even do that, you can see there's actually infinite many solutions here, okay? Now, when I restrict this between 0 and 2 pi, you can see there's only these two solutions, right? This is basically, if you remember, this is what we call the initial period of the cosine graph. So we have one solution at pi over 3 and 5 pi over 3, which I did find on that example. However, as we start to expand, if I said only the angles between 0 and pi, which I did, that was A, that's your answer. If I said all the angles between 0 and 2 pi, you can see those are our two solutions. But when I say all the solutions, now I'm asking for every single time that blue line crosses the red line. So how do you write that? Well, one thing we can look at is I kept on saying add 2 pi, add 2 pi, add 2 pi. And another way to look at that is look at the difference between these angles. Right? So if you pick angles that are on the same side of the curve, right? These are all to the right of the hump. Look at the difference between these. Here's pi over 3 plus 6 pi over 3 plus 6 pi over 3 plus 6 pi over 3. So if I keep on adding 6 pi over 3, I'm going to keep on getting to a solution. And what is 6 pi over 3 again? It's 2 pi. And you can do the exact same thing for all the solutions to the left. These are all 6 pi over 3 away from each other. You could even go to the left, right? So that's why we use n to represent that as an integer. So now let's go and look at the next solution. Okay, so the next solution basically had something a little bit more messy. So what I did is I did the work over here just to kind of break it up step by step, because I'm not always going to show the steps. But really, one thing I also reminded students too, if they have trouble using inverse operations or factoring or doing anything, like go back old school. Like how would you solve this equation? You would add the 3, you would divide by 4, and then you take the square root, right? So we're doing the exact same thing. We're just now solving for cosine of theta instead of x, all right? So you can see I added the 3 both sides, divided by 4, then I introduced the square root, and remember we have to include that plus or minus. Remember, using the rules of radicals, you can break that up to square root of the numerator over the denominator, and therefore that gives me cosine of theta equals plus or minus the square root of 3. So again, now to visualize, we have the positive as well as the negative. So in this example, we only had the positive, right? So we knew that the two angles had to be to the right of the y-axis. But when we have positive and negatives, then we basically want to find every single angle where the cosine of that angle is equal to plus or minus the square root of 3 over 2. So by looking at our unit circle or knowing our unit circle, we came up with all the angles that are on the interval or have a reference angle of pi over 6. So my first solution is find the angles between 0 and pi. Well, that's just going to be between 0 and pi. That's the first and the second quadrant. That's going to be pi over 6 and 5 pi over 6. As far as find the angles between 0 and 2 pi, that's basically everything that's visible on the unit circle. And so therefore that's going to be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now the next one is the all solutions, because one thing I told students as they're struggling with this, let's just put a big X there. As students are struggling with this, that they can just add 2 pi to all the angles. Because yeah, you could take all of these solutions and continually add 2 pi to them, right? So as long as you keep on finding these angles and adding 2 pi, you're always going to get back to a solution. But typically when we're doing a multiple choice problem or we want something in simplified, we want to see what is the least, the least amount that we need to write to satisfy all of these solutions. So I'll show it to you looking at it. So I'll show it to you looking at it using the unit circle, and then what we'll do is I will go back to showing it to you using the graphs or looking at the equation. So again, you can always add 2 pi to all of these angles. But if you notice, like this angle, the distance between this angle and this angle is half of a circle, which is pi. So if I take this angle, which is pi over 6, if I add pi to it, that takes me to 7 pi over 6. If I add pi again to it, that's going to take me to 13 pi over 6. You don't really need to know what those angles are. You just need to know if you keep on adding pi to those two angles, then you're always going to get a solution. And the same thing happens over here. If I take 5 pi over 6 and I add pi to it, I'm going to go back to a solution. And if I add pi again, it's going to take me to a solution. So even though you could take each and every one of these equations and keep on adding 2 pi to it, like over here, even though you can keep on adding 2 pi and adding 2 pi, in this case, since we have like some symmetry or we have two solutions that are equidistant from each other, we can just add that distance between them. See here, we had these two solutions were not equidistant to each other, so therefore we just added 2 pi. So let's go and take a look at the graph now to kind of compare this. All right, so back at the graph, same graph, we're doing y equals cosine of theta. I'm sorry. Yep, but now instead of intersecting with 1/2, we're going to intersect with square root of 3 over 2 and negative square root of 3 over 2. So you can see there's quite a little bit more solutions, right? There's actually twice as many solutions that's going on, at least between, certain intervals. Now, obviously, these are going to repeat on and on, forever. So we want to kind of let's look at this first within the interval. And then, so here's basically the initial period. And you can see, yeah, here's going to be double the solutions. We already had these solutions, or this is that's in the first quadrant. Then we have this solution, which is in the second quadrant, third quadrant, and then fourth quadrant, right? And you can see from 0 to 2 pi, there's 4 solutions. We doubled the number of solutions, which makes sense, right? For one line, you're going to have 2 solutions, 2 lines, now you're going to have 2. Now, the interesting thing is how do we understand that pi n instead of 2 pi n, right? Because when we had the 1/2, you could see that the distance was every pi. Well, now what we have is you can see that anything to the right of the hump here is now going to be pi away from each other. Let me zoom out a little bit. So you can see here, there's a solution, pi over 6, 7 pi over 6, 13 pi over 6, 19 pi over 6. So you can see that all of these angles are all pi over 6 away from each other, right? So instead of doing these two you could say, yes, could you still add 2 pi? Of course you could, right? You could still do the 2 pi game, add, 12 pi over 6, right? To get to the next one. But if you notice, if I just add pi, that takes me to a solution. Add pi takes me to a solution. So it's a little bit quicker. So, it's a little bit easier just to count by pi's than to do 2 equations counting by 2 pi. So hopefully that kind of made a little sense. We'll obviously be doing some more examples to hopefully refine that. So let's go ahead and now get into those lovely examples. Okay, so now we kind of have this idea of, if we have an equation with stuff, we isolate it. And we're basically going to solve all of our equations on the interval of 0 to pi, which is first and second quadrant, 0 to 2 pi, which is the whole unit circle, and then all the solutions. And just remember, if we have some symmetry, like some equidistant here, then we can use those smaller intervals to add up our solutions. So these are the problems that I gave my students that I'm just going to kind of work through, again, for them, and as well as kind of teach me step by step. So the main thing in this first problem we want to do is just isolate the sign. So all I'm going to do here is just divide by 2 on both sides. And therefore, I now have the equation sine of theta is equal to the square root of 3 over 2. All right, so I'm just going to sketch the unit circle here real quick. And I say, all right, sine is positive in the first and the second quadrant, right? So I have that angle and that angle, right? I know it can't be below. So it's going to be these 2 angles. Now I just need to remember what are my 2 angles here. Well, this angle here in the first quadrant is going to be, let's not write it in there. But you can see that these 2 angles between 0 and 2 pi is going to be pi over 3 and 2 pi over 3. Now again, for the next one, it says find all the solutions between 0 and 2 pi. Well, my 2 solutions are in the first and second quadrant. So my solutions are not going to change. So that's going to be pi over 3 and 2 pi over 3. All right, and then the next one is to find all the solutions. And again, we want to look for if they're equidistant. And again, the reason why this doesn't work in this example, like for instance, let's say this is pi over 3 away, right? So if you add pi over 3, you're going to get to the next solution. But if you add pi over 3 one more time, you get to the x-axis, which is not a solution to the equation. There's only 2 solutions to this equation, pi over 3 and 2 pi over 3 on the unit circle. So therefore, we can't just add some interval infinite many, n number of times. In this case, since they're not equidistant from each other, we're going to have to add 2 pi, and that's perfectly fine. We're just going to add 2 pi for each of these. Why did I change the blue? So we'll do, so this one's going to be theta equals pi over 3 plus 2 pi n, and theta equals 2 pi over 3 plus 2 pi n. How long am I using that? Oh, it's kind of, oh, I guess, oh, okay. All right, so for the next one, again, we want to isolate the tangent, and just remember that tangent squared of theta is the same thing as tangent of theta quantity squared minus 1 equals 0. Some people still kind of get that kind of confused with that notation. So the first thing we want to do is add a 1 to both sides. Then we have tangent squared of theta is equal to 1. Then we're going to introduce the square root, and we say tangent of theta is equal to plus or minus 1. All right, so now, again, going through our unit circle here, we say, all right, when is tangent 1? Now, tangent, again, tricks some students, remember the unit circle, because cosine was the x-coordinate, sine is the y-coordinate. And remember, tangent is the y over the x. So that angle is in terms of force here. So that is going to be the angle in terms of pi over 4. So my solutions for A here is going to be theta equals pi over 4. And again, I keep on going back and forth. You can write things as theta equals, or you can use them in the solution set. So either way is acceptable, at least in my class. So in this first two quadrants, I'm going to have pi over 4, and theta equals 3 pi over 4. Okay, so those are the two angles that satisfy there. As far as on the unit circle, it's going to be the same thing, but now I'm just going to add. So I'm going to have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now the next one is where it kind of gets a little tricky again, understanding these intervals. So here you could add 2 pi. Like I could rewrite each and every of these equations plus 2 pi, because if I take this angle and I have to add 2 pi to it, I'm going to get to infinite many solutions. If I take this solution and add 2 pi n, which represents the number of multiples or the integer, you can get infinite many integers or infinite many solutions. You could also do pi. You could take this angle and add pi to it, right? You could take this angle and add pi to it. But we can even get even better. So if you notice, these are equidistant to each other. From here to here, it's the same distance from there to there, it's from there to there, and then from there to there. So now we just got to ask ourselves, well, how far is it? How far is it from pi over 4 to 3 pi over 4? And you can say that distance is 2 pi over 4, or pi halves. So therefore, C, again, this is just going to be the simplified result, because I don't want to write every angle plus 2 pi n. That's like a lot of writing. Nor do I want to write two angles plus pi n. If I can avoid it, I would like to just write theta equals the first angle plus pi halves n. All right, let's continue on. So again, now these are going to have a little bit more inverse operations. Now we kind of have like two inverse operations going on here. So let's just go ahead and subtract 1. So just remember to undo addition and subtraction before undoing multiplication and division. So I have sine of theta. Oops, my bad. That looks bad. So sine of theta equals -1/2. All right, so knowing the unit circle, I know that sine of theta is equal to -1/2. That has to be in the third and the fourth quadrant. Hopefully you recognize these. There's going to have a reference angle of pi over 6. So therefore, it's going to be 7 pi over 6 and 11 pi over 6. However, if we look to satisfy this equation between the interval of 0 to pi, we notice that there's no angles, right? From 0 to pi, there's no angles. So we can say there's just no solution. Because any angle, any angle that we plug in those first two quadrants, sine's going to be positive. So you can see why that's never going to work. For B is all the angles on the unit circle. Again, this just comes into knowing which angles where the y-coordinate is -1/2. I like to think about it using reference angles. But at this point, you should just be familiar enough with the unit circle, hopefully, to be able to figure that out. And my solutions here, again, is going to be 7 pi over 6 and 11 pi over 6. Okay. Also, we can see that there's no equidistance between them. So therefore, I'm just going to have to take each angle and then add 2 pi to them. So 7 pi over 6 plus 2 pi n. And again, we have n because there's infinite many times we can add or subtract that 2 pi. So that'd be 11 pi over 6 plus 2 pi n. Okay, so next one, you think cotangent. Like when we do cotangent, like what's going on here? Did I do? Yeah, I did. Okay. So let's go and just isolate it first, and then we'll talk about it. Now, in this case, I'm also swapping the x with theta. I don't know why I did that. Oh, this one's missing an x too. Are these my last two? No, these are my last two. I decided to switch it up to x's. Interesting. All right. So let's go ahead and solve, though. Again, doing the same thing. We're going to add a 1. So then I have square root of 3 times the cotangent of x equals 1. Then I'll divide by square root of 3, divide by square root of 3. Now, here's where it kind of gets a little interesting here. So I have 1 over the square root of 3. You could go ahead and rationalize the denominator. There's nothing wrong with that. However, what I would recommend doing is saying, all right, if I know cotangent of x is 1 over square root of 3, remember our identities. Like cotangent and tangent are reciprocals of each other. So I could also just figure out tangent of x is going to be the square root of 3 over 1, or just square root of 3. So don't forget, you can use these identities sometimes to help you out. And hopefully you're a little bit more familiar with what tangent is than you are with cotangent is. Now, you could rationalize the denominator and do the exact same thing. Remember, cotangent is the x-coordinate over the y-coordinate, where tangent is the y-coordinate over the x-coordinate. Now, we do need to remember, though, what exactly these angles are. And a lot of students kind of forget the tangent, so let's just kind of do a quick little review here. Here's this angle that's going to produce square root of 3. That is square root of 3 over, no, that's not. That's 1/2, comma square root of 3 over 2. Okay, so when you take the y-coordinate over the x-coordinate, you get the square root of 3. So that's why that is our angle. Okay, so my preferred method is rather than trying to do x over y, which you could do, you just have to rationalize the denominator. And then when you take the x-coordinate over the y-coordinate, you would get square root of 3 over 3. But I think it's just easier to kind of know your tangents, especially at least for the first quadrant. So if we can see between 0 and pi, oh, I'm sorry. And for instance, last thing I forgot is tangent's positive, or tangent's positive, right? So remember, tangent and cotangent are only positive in the first and the third quadrant, right? Because that would be a negative 1/2, negative square root of 3 over 2. So these are the two angles that my tangent is going to be positive. So as far as what are my solutions in the first and second quadrant, that's just going to be theta equals pi over 3. As far as what angles are true, what are my solutions for my angles? Why am I using theta? It's x. Sorry about that. I just used theta for all the rest of these. So the solutions to my equation for the unit circle is going to be x equals pi over 3 and 4 pi over 3. And then for C, all the solutions, you can see that these are equidistant of each other, right? So let's just kind of do that in there real quick. Just do another color. We could say, hey, you can just keep on adding pi to each one of those, and you'll always go ahead and get that solution. So therefore, I'm just going to have x equals pi over 3 plus pi n. Okay? All right, doing good. All right, so now the next one, we're going to kind of mix it up here a little bit. Now you can see that we're dealing with more than one trigonometric expression in the equation. Now, in this first example, it's pretty tempting for students to want to multiply, right? You see like tangent outside of parentheses, like let's multiply that through. But again, our goal is to solve, right? We want to find the solutions that make this true. And since we have a product equal to 0, the best thing that we're going to want to do is apply the zero product property. That basically means set each quantity equal to 0. Now we can just go ahead and solve, or set each product equal to 0. So now let's go ahead and sketch this on the graph. All right, now when is tangent of theta equal to 0? Now remember, tangent of theta is equal to 0 at when the y-coordinate over the x-coordinate is equal to 0. All right, so we have negative 1, 0, and 1, 0. Each of these times when I take the y-coordinate over the x-coordinate, I'm going to get 0. So these two angles is going to be 0 as well as pi. All right, so 0 is an angle and pi. The next angle is when is sine equal to 1? Well, that's going to be at pi halves, right? Because we have 0, 1. All right, so we have these three angles. Now, remember the first quadrant, or this first restriction was from 0 to pi, where pi is not included. So we can't include this answer. So we're only going to include our first two solutions, which was 0 and pi halves. On the next equation, we're trying to find everything from 0 to 2 pi. So again, that's going to be 0 to 2 pi. But again, 2 pi is not included. So we have, 0, pi halves, pi. We don't have 3 pi halves because that'd be -1. And then we have 2 pi. Well, 2 pi is not included, so we can only include here 0, pi halves, and pi. Okay. Now on the final one for all the solutions, you can see that these are equidistant, right? But then if you add like pi halves one more time, you're going to get -1, which doesn't work. So what we're going to do is we have to treat these separately. You can see between 0 and pi, those are pi away from each other, right? And then at pi halves, we're just going to have to keep on adding 2 pi to it. So what I'm going to do is I'm just going to say theta is equal to 0 plus pi n. Well, really, 0 doesn't need to be included, so we can just theta equals pi n. And then our other solution is going to be theta equals pi halves plus 2 pi n. Okay? All right, so for the next one, you say, all right, well, now I have two equations. Now I have like sine and cosine, but, I could factor them. And if you factor them using the difference of two squares, that is factorable, but that's still not going to help you. Sine of x, minus cosine of x, difference of two squares here. That doesn't help you though. Because still you have to solve these equations. Like, what are you going to do now? Okay? So this is one that we're actually going to cover a little bit later on here. But the one thing I wanted you to think about is, again, kind of going back to that cotangent problem that I just did, is think about identities. Like I see a trigonometric function squared. I could rewrite either sine as cosine, or I could write cosine as sine. Now, it doesn't matter which one you want to do. I'd probably prefer not to distribute a negative just to not make those mistakes. So using my Pythagorean identities, cosine squared of theta plus sine squared of theta equals 1, I can rewrite sine squared as 1 minus cosine squared of theta minus cosine squared of theta equals 0. So by doing this, I now obtain 1 minus 2 cosine squared of theta equals 0. So now I can subtract a 1, and then I can divide by -2. So I have let's just do this step by step. Yeah, okay, that's fine. So then I have a -2 cosine squared of theta equals -1, divide by -2, just show all my work. Cosine squared of theta equals positive 1/2, square root. I already did this, so therefore that's going to be a square root of 1, or hold on, that's going to be a plus or minus, right? Let's just do it down here. Cosine squared of theta equals plus or minus the square root of 1 over the square root of 2, which equals plus or minus 1 over the square root of 2, which equals plus or minus the square root of 2 over 2. Oh, so we're kind of familiar with this. So our equation here is cosine of theta equals plus or minus the square root of 2 over 2. So we have done a problem, like this. If you remember, we did that for the tangent one. So again, we can see that cosine's always going to be that square root of 2 over 2 at our intervals of pi over 4. Okay, so if I want to find my solutions between 0 and pi, that's going to be pi over 4 and 3 pi over 4. If I want to find all the solutions between 0 and 2 pi, that's just going to be pi over 4, 3 pi over 4, 4 pi over 4, nope, not 4 pi over 4, 5 pi over 4, sorry. And 7 pi over 4. And then C, all the solutions, you can see that I can just take this first equation and add pi over 4 to it. So pi over 4 plus pi halves n. And there you go. So you can see it's the exact same equation like we did. One of the techniques to think about is if you have trigonometric functions, you have more than one, look to either, obviously here we didn't matter. We just applied the zero product property. Whereas here we used our identities to help us go ahead and solve that. So just some things to kind of think about for there. All right, so for the next two, you can see that we have more than one, but at least they're all sines and cosines. So now we got to think of like, what else can we do when we have multiple like variables? And again, the best technique or trick that I gave to students is remember what we did for solving equations. Like if I had more than one variable, x squared plus 2x plus 1, what did you do? You factored, right? And hopefully you recognize that what two numbers multiply to give you 1, add to give you 2. Well, that's 1 and 1, positive 1 and positive 1. This is a perfect square trinomial. This can be factored as x plus 1. No, let's do it this way. Yeah, that can be factored as x plus 1 squared. The reason why I bring that up is if you have trouble factoring this, like instead of trying to think sine of x times sine of x, like write it as x's. And then all you got to do is just go back and convert and replace or substitute back in sine of x in for x. Because the factored form of this is sine of x plus 1 quantity squared equals 0. Right? And the more you do these, the better you'll get at this. But again, if you like have trouble with this, just go back to the x's and do it that way. Now in this case, we're going to square root both sides, and I'll have sine of x, plus 1 equals 0, and subtract and subtract. And therefore I have, in this case, sine of x is equal to -1. And if I was going to find on these intervals, again, -1 on the unit circle is all the way down here, right? So it's not on the interval of 0 to pi. So for A, there is no solution. Come on. For B, the only solution is 3 pi over 2. So I'll just say theta equals 3 pi over 2. And then for C, all the solutions, that's going to be theta equals 3 pi over 2 plus 2 pi n, right? Because there's only one that's solution, so I got to keep on adding 2 pi to it. All right, so for the next one is a factoring problem that's obviously not easy for many students to work on. So that one's going to be 2x squared plus x minus 1 equals 0. But again, the way I want to bring it up to students is, we know if this is a quadratic trinomial or a quadratic, and it's a trinomial, all trinomials can be factored into a product of two binomials. So let's factor this as 2x and x. Okay. Now we're thinking what two numbers multiply to give me a -1? Well, that's going to be -1 and 1 and +1 and -1. -1 and yeah. So we just got to figure out where's the positive and where's the negative. Is it +1 here, -1 here, or is it -1 here, +1 here? Now, you can always do guess and check. But the way that I think about this is I look at the middle term. If the middle term's positive, that means the product of my products, that means the sign of my product. So I have two products. So I'm going to be the outer and the inner. So the 2x times this number and the x times this number. Whichever one is larger, which is going to be this one, needs to be positive. That means I need to multiply that by +1 and that by -1. And again, let's check our work. 2x times x is 2x squared. -1 times 1 is -1. This gives you a -x. That gives you a positive 2x. 2x minus x is x. So again, here's my factored form in terms of x's. Now let's just replace x with cosine of x. Okay. Now I have a product equal to 0. I can apply the zero product property. Okay. So now I just use my inverse operations here. All right. Now, based on the unit circle, let's see here. We have 1/2. 1/2. Where is 1/2? We have up here, and we also have 1/2 is going to be, that's a 1. Did I do that? Oh, that's supposed to be a +1. I was wondering, I was like, did I do that wrong? Yeah, it's supposed to be a +1. Okay, so we have 1/2 here, and we have 5 pi, or 1/2 down there, and then we have -1 here. Okay, so there's my three solutions here. We got pi thirds, pi, and 5 pi over 3. So as far as my solutions go from 0 to pi, again, this is not included on the interval. So for A, my only solution here is going to be pi over 3. For B, my solution is between 0 and 2 pi. is going to be the angle pi over 3, pi, and 5 pi over 3. Now the next one, you can see that these are actually equidistant from each other. From pi over 3 to pi, you can see that distance is 2 pi, right? Because how far does it take you, how far is it from pi over 3 to 3 pi over 3, which is pi? Well, pi plus 2 pi over 3 is 3 pi over 3. And then if you go from 3 pi over 3, which is pi, to 5 pi over 3, that's another 2 pi over 3. So you can see, again, going back to that problem that we worked on, these are equidistant of each other. Okay, so if we keep on adding 2 pi over 3n, we're going to keep on getting to the next solution. So all I got to do in this case is just go ahead and take pi over 3 plus 2 pi over 3n. Okay, so that's how we solve the equations when we just have one variable and using inverse operations. Now we're going to look at what happens when we have multiple angles. So one of the things I talked with my students to discuss was, how does the following solutions change based on the transformations? Like, we already know the solutions to this equation. How are they going to change when I have, numbers in front being multiplied like 2 and 3, or when I divide by like 2 and 3? So you can see in these next couple equations that we are basically dealing with some transformations, right? And we need to remember what exactly is the transformation that is being applied to this function. And again, this really goes back to what we previously talked about in our transformations of functions. When we're multiplying by a scalar inside of the function, that's a horizontal compression. And if you remember what we talked when we graphed the trigonometric functions, what that did is that actually changed the period of the cosine graph. That actually compressed the graph. Whereas when we're dividing by 2 or a 3 or multiplying by a fraction, what we're doing is that's actually a horizontal stretch. So, and that also elongated the period. So let's go and take a look at the graph, and you can kind of see how that's going to change our solutions. So here we have the cosine graph, and you can just see there's a nice little cosine, all right? And then we previously had all the solutions here, and you can see again from the first example we did pi over 3 and 5 pi over 3. Now, let's kind of go back and let's see what happens now. Well, here's all my solutions. So let's go and see what happens when I compress this by 2. You can see this graph is being compressed, right? And if I did it by 3, you can see it's going to be compressed even more. Now, what's more important about that is understanding the solutions, right? So sometimes it's a little bit easier to see, and actually I'll kind of go through this again. But you can see now, if I divide by 2, you can see how that is elongating the graph. Now, this is a lot to kind of take in on just one graph. So what I'm going to do is instead of showing everything, I'm going to show these transformations only on the initial period from 0 to 2 pi. So that's what I did here. And you can see that what that did is I went from having 2 solutions, right, to having now 4 solutions. 1, 2, 3, 4. Now, you can see a little bit of the relationship here from pi over 3 to pi over 6 to that looks like you're just going to be dividing by 2. But that's not the case for every single one. Like 5 pi over 3 to 5 pi over 6, it looks like you're just dividing by 2. But you can see that doesn't work for every single solution. And then also, if I add, or if I divide by 2, you can see I went from 2 solutions now to only 1 solution, which is 2 pi over 3. However, you could see that from my original solution, pi over 3, I am just multiplying it by 2 to give me 2 pi over 3, but there's only that 1 solution. So the main point that I'm trying to get is that when we have trigonometric functions that we're solving for what we call multi-angles, we need to understand what those values are doing to our not only our graph, but to the solutions. If with no compression or stretching, we have 2 solutions, right? We just need to understand when we compress the graph or multiply by 2, that is going to add, not that one, where it's going to add 2 more solutions to our equation. Or if I'm dividing by 2, that is actually reducing it by 2. So, and obviously this gets a little bit more messy as we get into dealing with infinite many solutions, right? And you can see how this is going to repeat itself from there. So that's what we want to do. We can see, hopefully you can see this graphically. Now let's go and look at this from the algebraic approach. So from the algebraic approach, basically we're going to do the exact same thing. Now I'm going to solve these on the interval of all solutions in 0 to 2 pi. I'm not going to deal with from 0 to pi. Now, really the main thing that we're going to be doing, and again, one other way you could do this, which I didn't teach in this class, but you could also just use, substitution and just solve for alpha, equals -1, and then just say alpha is equal to 2 theta. So if you don't like solving for 2 theta or theta divided by 2, then you could always use a different variable and then substitute that back in. But just for the sake of keeping things simple, you're going to do the exact same thing. You're going to say, all right, the sine of 2 theta, just like it was theta though, sine of 2 theta is equal to -1. So what angles would make that true? And obviously the only angle that makes that true is 3 pi halves. But what I'm doing here is I'm solving for all solutions first. So I have 3 pi halves, right, equal there, and then I'm going to find all the solutions. So I'm going to add 2 pi n, right, because I have to have infinite many of those answers are going to give me 2 pi n. So I go ahead and solve that. I add 2 pi n. Now, again, though, we never solve for 2 theta. Like in algebra class, we didn't solve for 2x or x divided by 2. We solve for x, right? So what we're going to do now is once you have set your equation, solve for all solutions, then you divide by 2 to solve for theta, or multiply 2, whatever you need to do to isolate the theta, whatever transformations. It actually could be any transformation, adding, subtracting, whatever. But then you can solve for your theta, and now you get the equation 3 pi over 4 plus pi n. Now what this helps us do, and that is going to be all the solutions. You can see how I kind of switched it up. Oh, actually, I noticed that my examples, I switched them up in order. So it's easiest to solve these equations for all solutions first, and then to go backwards and find all the solutions between 0 and 2 pi. Now the way to find 0 and 2 pi, we just need to pick intervals of n, right? Because we know we have 3 pi over 4. That's the first solution. And in this case, we can add pi n. Well, how many times could we add pi n? We're going to add pi, or just pi, right? For different numbers. We're going to add pi as many times as we can, as long as it's between 0 and 2 pi. So when n is 0, I have 3 pi over 4. When n is 1, I have pi, right? So pi in terms of force is 4 pi over 4. 4 pi over 4 plus 3 pi over 4 gives me 7 pi over 4. I can't add pi again because that would take me to 11 pi over 4, right? If you add 7 pi over 4 plus 4 pi over 4, that's 11 pi over 4, which is larger than 2 pi. Because remember, in terms of force here, we have 0 to 2 pi is 8 pi over 4. So you just want to make sure that you remember, put 2 pi in terms of those constraints. For the next example, again, now we have a little bit of operations, which is fine, right? Just subtract the square root of 3 over 3, and then we have tangent of theta divided by 2. We need to know when that triangle, when that's going to be true, and hopefully you recognize that it's going to have the reference angle of pi over 6, but tangent's negative, so we know it has to be in the second quadrant as well as fourth quadrant, right? It can't be in the first and the third. That's when tangent's positive. And we recognize, though, for as far as all solutions, it's just going to be 5 pi over 6 plus pi n. But again, that's for theta divided by 2 equals 5 pi over 6 plus pi n. So then to solve for theta, I multiply everything by 2, which gives me 10 pi over 6, which is 5 pi thirds, plus 2 pi n. Make sure you multiply the 2 times everything. And then to find all the solutions, again, we just use different values of n. So when n is 0, we have 5 pi thirds. When n is 1, though, we have 2 pi. Well, 2 pi in terms of thirds is 6 pi over 3. 6 pi over 3 plus 5 pi over 3 is 11 pi over 3, which is way over 2 pi over 3. And again, like that makes conceptual sense, right? If we know there's only one answer on the unit circle and I'm compressing the graph, I should have more solutions. If I know there's only 2 answers on the unit circle and I am stretching my graph, then I know I'm going to have less solutions, right? So you can see how this kind of makes sense by understanding those graphs we looked at. All right, so now I'm just going to kind of work through, let's see, 4 examples, and then we'll be all set. All right, so first example, we have sine squared of 2 theta equals 1. So again, in this case, all I'm simply going to do is just solve for sine. So I'm just going to take the square root of both sides. So I have sine of 2 theta equals plus or minus 1. And again, now we're just trying to identify, when is sine equal to plus or minus 1. So we can say 2 theta, right, is going to equal on the unit circle. It's equal to 1 here and here. So we have these 2 angles, which is equal to pi halves and 3 pi halves. But notice how they are pi away from each other. So therefore, I'm going to say plus pi n. And you can see why this is so helpful, because if I wrote both of these equations, if I did both of them, then I'd have to divide by 2 twice, and it's just so much more work. So it's nice to be able to see that they have that plus pi n, because now I can just solve divided by 2, and theta equals pi over 4 plus pi halves n. Now to find all the solutions between 0 and 2 pi. When n is, you're just going to basically start at 0 and then keep on adding intervals of pi halves until it's larger than 0 to 2 pi, which would be 0 to 8 pi over 4. So when n is 0, I have pi over 4. When n is 1, I would have pi halves, which in terms of fourths is 2 pi over 4. 2 pi over 4 plus pi over 4 is 3 pi over 4. And hopefully you kind of recognize this to be that same thing. We could add 5 pi over 4, and then we could do 7 pi over 4. Right? But I can't go past 7 pi over 4 because that would be, if I added another pi halves or 2 pi over 4, that'd be 9 pi over 4, which would be larger than 2 pi. All right, for the next example, again, just to solve, we're just going to divide by a 4 here. So then I have cosine of theta divided by 2 equals square root of 3 over 2. Okay, now again, remember this is the positive version here. So that's going to be positive square root of 3 over 2, and over here, positive square root of 3 over 2. So therefore, those two angles I have two different angles, and they're not equal to each other, or they're not equidistant from each other. So I'm going to have to write them both out. So I'll say theta divided by 2 equals, let's see, that's going to be pi over 6 plus 2 pi n. And then I have theta divided by 2 equals 11 pi over 6 plus 2 pi n. Okay, now, again, to solve for theta, I'm just going to multiply everything times 2. And I have to do that thing over here as well. So when I multiply everything by 2, I get theta equals 2 pi over 6, which is pi over 3. Plus 4 pi n. And here I get theta equals, let's see, that's going to be a 22 pi over 6. Was that square root of 3? I don't remember that answer. I guess I remember. That's 11 pi over 6. That's 12 pi over 6. That is correct. Cosine's both positive. Okay. Which reduces to 11 pi over 3 plus 4 pi n. Okay, so that is going to be all of your solutions. And then if I just want to find the solutions between 0 and 2 pi, again, when n is 0 for both these equations, I have pi over 3 and 11 pi over 3. But again, if I want my answer between 0 and 2 pi, I can't add 4 pi, right? When n is 1, I'm adding 4 pi. So that's not going to work, right? You can see that the I'm only going to have 2 solutions again in this case. Oh, that's right. No wonder. I was like, 11 pi over 3, why does that not work? 11 pi doesn't work because 11 pi over 3 is already larger than 2 pi, right? Again, I was trying to find the solution. That's finding all the solutions. But when I just want to find the solutions between 0 and 2 pi, 11 pi over 3 is already too big. So therefore, I can't include that. I can include it in all solutions, but I'm not going to include it in the solutions from 0 to 2 pi. And again, that makes sense. Like if you look at the unit circle, there's 2 solutions. So if I'm horizontally stretching the graph, I should have 1 solution. All right, last 2 examples here. So in this one, it looks like, whoa, I got a lot of tangents going on here. And again, if we want to look at this, we say, all right, I can't use my inverse operations, so maybe I should try factoring. And again, what we want to do is say, all right, what do these 2 expressions have in common? Well, they have a tangent of theta in common. So when you factor out a tangent of theta, you're going to be left with a tangent of 2 theta plus 1 equals 0. So I have tangent times tangent of 2 theta plus 1 is equal to 0. Now I can set them both equal to 0. So tangent of theta equals 0. And tangent of 2 theta is equal to a negative 1. Now let's go ahead and sketch this on the unit circle to kind of see where this works out here. So tangent is going to equal negative 1 here in the second as well as the fourth quadrant. Tangent is going to be equal to 0 when tangent is 0 as well as in pi. So you can see here I basically have 2 angles that are pi away from each other, right? I got these 2 and I got those 2 angles. So they're both pi away from each other. So as far as finding all the solutions here, I could say I have, well, actually this one is just my two solutions is going to be theta equals pi n, right? It's really 0 plus pi n, but you can see that 0 and pi are just pi away from each other. And then this one is going to be 2 theta is going to be, that's when tangent is equal to -1. That's going to be 3 pi over 4 plus pi n. All right. Now this one I already solved, 0 equals pi n. And then this one I just need to divide by 2 here. So I'd get theta is equal to 3 pi over 8 plus pi halves n. All right, so that's going to be all the solutions. So I have my theta and my other theta here. And then to find just the solutions between 0 and 2 pi, or pi n, I know I have 0 and pi. I can't include 2 pi, right? When n is 0, I have 0. When n is 1, I have pi. But n is 2, I have 2 pi, but that's not included on the restriction, right? Because it was 0 to 2 pi. So as far as all the solutions go, I'll have 0, pi. When n is 0 here, I have 3 pi over 8. When n is 1, I have pi halves. Now, pi halves is the same thing as 4 pi over 8. So therefore, that would be 7 pi over 8, right? It's important to recognize that pi halves is equal to 4 pi over 8. So that's really what I'm adding. I'm taking 3 pi over 4. When n is 1, I have plus 4 pi over 8. When n is 2, I'm going to be adding 8 pi over 8, right? Because 8 pi over 8 is pi, which 2 times pi halves is pi. So if I add another 4 pi, I'm going to have 11 pi over 8. I can add it again, which is giving me 15 pi over 8. But I can't go any higher because, again, 2 pi is equal to 16 pi over 8. So remember, you can only go as the restriction is from 0 to 2 pi. So you can see how that is now going to be our solution set. All right, last example is using the secant of theta halves plus 2. So again, let's go ahead and solve for secant. And therefore, we have secant of theta divided by 2 equals -2. Now, you could go ahead and figure out secant is, 1 over x, but I think it's a little bit easier just to use the reciprocal identity and say, all right, if secant of theta halves is equal to -2, then cosine of theta over 2 is equal to a -1/2, right? Because remember, those are reciprocal identities. That's how these reciprocal identities can help us here. So again, they're just the reciprocals of each other. So now let's go to the unit circle and say, all right, when is cosine equal to -1/2? That's going to be up here and over there, right? Because cosine's negative, so it's going to be to the left of the y-axis. So those are going to be two angles. They're not equidistant from each other, so I have to write them both out. So therefore, I'll have theta divided by 2 is equal to, let's see, what is that? That's going to be 2 pi over 3 plus 2 pi n. And then I have theta divided by 2 equals, let's see, 4 pi over 3 plus 2 pi n. Okay, so let's multiply everything by 2 again to solve for theta. So now I have theta equals 4 pi over 3 plus 4 pi n. And over here, I have theta equals 8 pi over 3 plus 4 pi n. So again, you can see that we have some extra solutions, right? So the only solution that's going to work, that's going to fall between 0 and 2 pi, here's all my solutions, but the only one that's going to satisfy between 0 and 2 pi, which would be 0 to 6 pi over 3, is going to be, let's write it as theta equals 4 pi over 3. So that's the only solution that satisfies the requirement of 0 to 2 pi, which in terms of thirds is going to be 0 to 6 pi over 3. So there you go, ladies and gentlemen. That is how you solve trigonometric equations. We did a lot of examples. We did the reciprocal functions. We did double angles. We did half angles. We did factoring. We did inverse operations. We talked about different intervals from 0 to pi, 0 to 2 pi, as well as how to find all of the solutions. So I hope this was helpful. And if you had any questions on any of the content, then please feel free to add any comments down below. And either I or hopefully somebody can be able to answer your questions. And I will look forward to seeing you on the next video. All right, cheers.